So in our last activity, we rolled a ball down a hill from rest and measured the various distances and the times for those distances to determine how fast the ball was going at the bottom of the hill and what the acceleration was of the ball on the hill. And then we made some graphs. So we used our kinematic quantities here. And we chose that speed to be 0. We released the ball from rest. And we chose displacement and measured those guys. And then for each displacement that the ball was rolling down the hill, we measured the amount of time that it took. And what we did was we chose the displacements to be evenly spaced. And what we ended up finding is that the times were not evenly spaced. And we used that to calculate the final velocity and the acceleration and to make some graphs. So we turned this into graphs, and we determined, based on our displacement versus time graphs, that we got a curve which says that displacement is some constant times time squared. And when we made our velocity versus time graph, we found that the velocity is linear, and that means the velocity is some constant that we usually call slope times time. And what we found was this slope here is the acceleration. And what you may have noticed is that this constant is 1/2 of the acceleration. In the Law of Falling Bodies video, they showed a few things, and one of them was a penny and feather falling side by side first in air, and you could see that the penny fell straight down and the feather kind of floated down, and they fell differently. And then they sucked all the air out of that chamber, and they dropped them again, and they fell side by side, and they showed that the air has an effect on things that are falling. But if you're going to use something that's very dense, like a hunk of metal, air resistance is almost not relevant, almost. So you can pretty much ignore it for the motion of that thing. The other thing that that penny and feather experiment showed is that the acceleration is pretty high relative to what we can record. So for this ball rolling down a hill, I can record, and you can record, the distances and the times as long as that hill is shallow enough. And in the Law of Falling Bodies video, they mentioned that Galileo did this experiment where he took shallow hills and then he made it steeper and redid the experiment. What we're going to do here is we're going to skip the whole getting steeper part, and we're going to go straight to, let's just drop it straight down. Let's do the penny and feather, and the question is, well, what is that acceleration that is due to gravity on the object? And we're going to try to eliminate air resistance or ignore it. I mean, I can't suck the air out of the classroom and then do the experiment with me in here. That wouldn't work very well. So I'm just going to use this 500-gram weight. It's about a pound, and since it's dense brass, air resistance should be roughly irrelevant. And we're going to go through the same things, except this time we're not going to do a power series fit in our graph. We're going to go straight to the polynomial because we already know that this is a t squared. We don't need to discover it anymore. That's what the point of this experiment was, to discover what the relationship is between distance and displacement for an object undergoing uniform acceleration. Now the question is, what is that number? What is that acceleration that's due to gravity when we drop an object? Now, it's going to fall way too fast for me to be able to say, okay, I'm going to drop it for this 20 centimeters and I'm going to time it for this 20 centimeters. That's not going to work. So what I have instead is a ticker tape timer here that plugs into the wall, and it's got a motor inside that's going to make this hammer vibrate up and down 60 times a second, and it's going to hit a little metal anvil. Maybe you can see that shiny thing there. Little metal anvil 60 times a second. So every single dot that it's going to make, because I'm going to put this piece of carbon paper in between the hammer and the anvil. So the hammer is going to hit the top of the carbon paper, and then I have ticker tape paper that the weight is going to pull through there, and it's going to make dots on the ticker tape paper. So every single dot is now going to be a 60th of a second. So what we did last time was we choose the distances 20 centimeters apart on the meter sticks, and then we measure the times. This time what we're doing with this machine is we're choosing a 60th of a second for the times, and now after that we're going to measure the distances, and we're going to see what the relationship is that way. We've reversed it because we can do it now with this little device. So let's take out, and we're going to get a bunch of dots, and we don't need all of them. So sliding the ticker tape paper underneath the carbon paper, and then I need to tape that, and let's move the camera over so I can show dropping it, because this is not going to work just to hold it up in the air and drop it. I'm going to need to brace it against something, and we'll see how this goes. 50% chance the paper rips, but I'll just try again if it does. All right. Paper didn't rip. It got pulled all the way through. Notice how fast that was, but we have dots. We have dots on here. I like it. So some of the dots are very, very faint. There's no way, oops, fortunately I didn't need that part. Some of these dots are very, very faint. There's no way you're going to be able to see this on the camera. So I'm going to switch to a close-up view, and I'm going to pen these dots a little bit darker, and then discuss what the pattern is that we see and make some graphs. All right, I've used my red pen to darken the dots, and I've also drawn some lines up to the edge of the ticker tape paper so you can see how it matches up with the meter stick. And here, let me pull it tight because there's a little gap there. And we can see the first, let's see here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got 11 dots on there. And what we're going to do is we're going to measure the distance from the 0 dot to each subsequent dot. So from 0 to 1 is about 1.5 millimeters. Then 0 to 2 is a little over 0.5 centimeter. And then from 0 to 3 is about 1.25 centimeters, and so on and so forth, always from the 0 dot. And we're going to put that in our spreadsheet and make some graphs and look at the relationship among the displacement, velocity, and acceleration graphs. To help us finish out our data table, we have, and I'm going to show this in a minute, displacements and times. And we're going to use our kinematic relationships that we've previously developed. So S equals VOT plus 1/2 AT squared, and VF equals VO plus AT. We're going to use these guys to determine these based on the specifics of, we chose that to be 0 because I dropped it from rest. And then we measured those, and we know that that's a 60th of a second for each dot. So we're going to use, for this guy and for this guy, actually for this guy, we're going to use this one and not have to go through the acceleration. I'm going to use this because it involves this guy that we chose to be 0. So we can figure out that the final speed is 2s over t. For each dot, the weight has fallen a certain amount of distance, and from rest down to that distance it will be moving at a speed according to this relationship because we've measured the distance and the time was a 60th of a second from 0 for each of those dots. And then the acceleration is going to be that how much time did it take to reach that speed. And this will smooth out all of the little imperfections in the motor that exist, because this device is pretty old and you probably don't have access to it, which is why I'm just demonstrating this one. That'll smooth out all of the little variations that exist, because it's a 60th of a second plus or minus a little bit of wiggle, because it's a physical piece of equipment and it's not perfect. So this will cover over those little wiggles and smooth them out just a little bit, so that we can get a better picture as to the relationship and what's going on here. So let's switch and start taking a look at the data table and then make some graphs. Here's our data table with my measurements. That last digit is a guesstimate. If you paused the video and made your own measurements, you're likely to have a slightly different last digit estimate. That's okay. And we're going to use those relationships that I just noted on the board. And realistically, we're not going to get too much more than that. And I dropped this from 0, so we're going to type that in. If I type that formula in for that top one, I would be dividing by 0, and Google Sheets and Excel don't like that. The acceleration is going to be that final velocity divided by the amount of time that it took to get there. And now we're going to make some graphs as we've done before. So select the times, hold down Control, select first the distances, insert, chart, and this is going to be off screen. Let's see if I can move this over. You can see the things that I select because I want time there and I want only distance on that axis. I'm going to scroll up, and I don't want a column chart, I want a scatter plot, and we have a very nice curve there. We will go down to Customize, Series, Trend Line, and you should notice that it is definitely not linear. What we want is polynomial. Let's take a look at the equation. Now, if I move this to its own sheet, and we come over here, we can just put that in the center there. We have a nice curve upward. 1/2 of the acceleration goes with our quadratic term, so we have 438. Doubling that should give us our acceleration, which is 876. That's a little bit lower than it should be. It's about 10% lower than it should be. But given the age of the equipment that we're using, that's not terribly surprising. So let's make another graph here. Select, hold down Control, select again. And we will go up to Insert, Chart. And once again, the computer has decided to give us a bar graph. We don't want a bar graph. What we want is a column chart. We don't want a column chart. What we want is a scatter plot. And then we will customize, series, trend line. Now this one is linear. Let's use the equation. And this one is telling us that the slope is 879. Now a slope of 879 is not too far off of 876. And we'll put it on its own sheet. Let's make one more graph. Select the whole thing. Now hold down Control, drag and select. We will insert another chart. This one, they gave us time acceleration on a scatter plot. And now let's go to Customize in Series and Trend Line and show the equation. And we have a y-intercept of 981. But we also have a negative slope. Ideally, that slope should be 0. So this acceleration is going to be a little bit off, not terribly surprising. but we do have general relationships shown here.